To the video explaining multi-threaded solver for combinatorial logic puzzles by Andrew Browning, Om Patel, Kyle Seni, and Andy Van. Today, we'll be diving into the world of parallel puzzle solving, specifically through multi-threading. The project focuses on applying multi-threading techniques to two well-known logic puzzles, Sudoku and nanograms. For Sudoku, we're relying on backtracking, and for nanograms, we're implementing a depth-first search approach. What's most interesting is not just solving these puzzles, but comparing the performance trade-offs between running the algorithms sequentially versus in parallel. We ran experiments across standard 9x9 Sudoku boards, ranging from easy to hard, and across various nonogram sizes to evaluate the benefits, and the limitations of threading in real-world scenarios. So, before we talk about the algorithms, let's quickly cover what these puzzles are. First up, Sudoku is a 9x9 grid that's divided into 3x3 subgrids, and the rule is pretty simple. Each number is from 1 to 9, and it must appear exactly once in every row, column, and 3x3 box. Sounds pretty easy, but the difficulty can escalate pretty fast. The goal is a unique solution that satisfies all of these constraints. Now, nanograms, a bit less mainstream, but they're still pretty fascinating. You're given a grid along with numeric clues for each row and column that describe how many blocks of filled-in cells appear and also in what order. But the twist here is that these cells are binary, so they're either filled or empty, and your job is to deduce the picture by interpreting the clues correctly. Both puzzles share something in common. They're constraint satisfaction problems, and solving them efficiently is pretty computationally intensive. So both Sudoku and nanograms fall into like a broader category known as constraint satisfaction problems. And in this formulation, you're given a set of variables, each with a domain of possible values, and a set of constraints that must be satisfied. The challenge lies in the combinatorial explosion. The number of possible configurations grows exponentially, especially as the puzzle difficulty increases. So traditional brute force methods are computationally expensive, and they're really impractical for like more complex puzzles. So multi-threading becomes very useful here. So the big question we asked was, can we leverage parallelism to reduce the solve times? Even with the overhead of managing threads, could there be a net gain in performance? And this project basically sets out to answer this question.
Hi, I'm Andrew, and I'll start explaining the background and relevant work. So let's start with a bit of background and the research that influenced our project. We built our work on some well-established techniques. For example, in solving Sudoku, traditional methods like backtracking and even more advanced approaches such as algorithm X with dancing links have been really effective. One interesting point we found in the literature is that how you order your candidate numbers can make a huge difference. So whether you stick with a fixed order or use randomization for a more unpredictable approach, it can really affect your overall computation time. On the nanogram side, researchers have used depth-first search and even smart reductions to 2SAT to handle the constraints of these puzzles. These methods show us that these can be really challenging combinatorial puzzles, and it sort of sets the stage for exploring if adding parallel processing can boost performance. We really wanted to see if multi-threading could help handle these exponential search spaces and search them more efficiently. So now let's move on to our parallel methodology. For the Sudoku solver, we noticed that checking if a number fits in a cell boils down to really three independent tasks. First, you need to check the row, then you need to check the column, and then finally the 3x3 subgrid. So why not have each of these checks running at the same time? We can split these into separate threads, so while one thread is busy checking the row, another checks the column, and the third handles the subgrid. This allows us to work on multiple parts of the problem concurrently. For the nanogram solver, the situation is a little bit different. Since we're using a depth-first search to navigate a huge search tree, the idea was to divide this tree early on. We let different threads handle different sections of the search tree or different branches, and we use asynchronous calls, futures, and atomic variables to manage communication. So if one branch finds a valid solution, it tells the others to stop. Okay, next I'm going to explain some of the implementation details. For our Sudoku solver, we spent most of our time working on the isValid function. Instead of performing row, column, and subgrid checks one at a time sequentially, we created separate threads for each check. Once each thread completes its task, we join the results together to determine if the placement is valid. And then for the nanogram, like I said earlier, we used a DFS-based exploration strategy, and we made sure to do early division of the DFS tree for our parallel processing. And then beyond that, we use C++ for our language of choice, and we use kernel library for measuring the execution time of our different methods.
The README contains a summary of our research info and also how to compile the program, as you can see here. And I will go more into the specifics of the input format. It's listed here, but when I run the source code, I will walk through it. So let's go into the research. Here's a report. And we talk about the background of each puzzle. So we are dealing with two types of combinatorial logic puzzles. One is Sudoku. So Sudoku is normally in a 9x9 format, as seen in this visual here. And it comes with cells already filled out as clues, and then empty cells, which can be filled with the number 1 through 9. Sudoku grid is considered complete after following all these 3 rules. That it's all filled out with number 1 through 9, and that every row they must all be different, basically. So this row, it could be 1, 4, 2, 3, 9, 7, 6, 8, 5, basically. The same number can't appear twice, so it can't be like 9 in this instance. And the same criteria applies for each column, so like from top to bottom, and for each subgrid. And a subgrid is defined as this 3x3 subsection that is outlined here, the whole entire puzzle. For our program, we are dealing with the standard 9x9 puzzles. There is a computability problem with dealing with n by n, but we are dealing with just a standard to limit our scope, and we are going to deal with input cases that range from easy to hard. Typically, easier puzzles have they have less clues. No, easier has more clues filled in, so more numbers, which makes less guesswork and more constraints that narrow down the solution. And then hard is the opposite. There'll be less clues and more open spaces to deal with. So that's Sudoku. Let me talk about nonograms. Nonograms, they're also known by Picross, paint by numbers. We are dealing with different dimensions with these puzzles, so they can be n by m, meaning it could be like 5 by 20, basically. And it can vary. We're dealing with varying dimensions for this problem. And basically, each row and column has clues associated with it. And the rule is that, let's say this first row, it has 2 and 1. From left to right, it must have a section of 2, then a gap in between, at least by 1 gap. In this case, there's a 3 gap. And then a filled slot here of 1. And this has to follow for each row and each column. So these are the constraints for the problem. In this case, this is a 6x6 nonogram. Now let's go over methods to solve each of these. We're going to start with Sudoku. So the most common easy to implement method is brute forcing. We do this by backtracking, basically. We run through every empty cell that's in here, and we validate it. Basically, we start from the top left, and we work all the way down to the bottom. And if it's not valid, we backtrack through recursion, and then try the next value that will try to validate it. Eventually, after guessing through an order from all these cells, it's going to find a solution that matches all the criteria described above. So, let's see. We decided to just go with the normal approach of guessing from 1 through 9 instead of going to the stochastic approach, because we believe it wouldn't make much of a difference for our comparison test between, because we were trying to figure out whether sequential or parallel implementation could be faster for this type of puzzle. So we did not bother with implementing the stochastic approach. But basically what that does is when we brute force guess for each cell, we pick a random available candidate instead of going from the order 1 to 9 in a loop. Now, another method for solving Sudoku is algorithm X, and this basically converts it to an exact cover problem. And we use a dancing links data structure, which is basically a circular double linked list. And here's a lot of info about it. We did not decide to implement this as we believed it would be hard to parallelize, but it definitely has more capability too than backtracking. Now, nonograms has two methods we found out here. The satisfactory problem, we turn it into a similar problem of like binary images. Basically, these nonograms have filled cells and unfilled cells, and that can be ascribed to, analogized to a discrete tomography problem, where we actually deal with the amount of filled sums for the horizontal and vertical lines, because it basically is just a binary image of unfilled and filled cells. And we can break this down to make a dependency graph and solve this for each pixel. And that describes it to a constraint satisfactory problem. Now, our method we chose to implement was DFS. It is similar to our backtracking method for Sudoku, but we figured we'd have more opportunity to split the workload by dividing the branches, and I'll elaborate what I mean by this. So for nonograms, what we do is we choose subtrees of recursions to divide the threads into. And this helps, since there's a lot more constraints that can be listed rather than just like the 9x9 grid of a Sudoku. As you can see here, you basically dedicate a thread to go through, have a local copy of the board, and then validate through the our DFS search to see if it's true. If one thread possibility basically solves the puzzle for us, we have like a shared boolean called nonogram solved, and one of them sets it to true, then the rest will stop early, and that speeds up things. Now back to Sudoku, we decided to parallelize the is valid part, and basically this checks the criteria for one, the subsection, the cells, and the rows, the columns and the rows, I mean. And we can see, and it basically just spawns 3 threads that goes through all these checks that can be done parallel. It does not rely on like previous cells, of course. So we figured this is a good parallelization point for us in this implementation we have. So that is our summary of our implementation. I'd like to show you the program now and how we structured it. So what we have here is our program, and has capability for both the parallel and sequential methods. So let's start with Sudoku. So Sudoku is always 9x9, and we have a class for Sudoku. We have a current board and a completed board. So this is going to be what we work on, and completed boards for the reference that we'll show in the input. We read the input from our input file, and this is a good time to show you the input file. So a Sudoku file will always have no, it's a 9 by 9 dimension, so we don't have to specify on top. At first is the working puzzle. So this is the puzzle with the blanks, not filled out yet. So it's nine lines, 9 characters each. A blank represents a blank cell, and then the other numbers represent those are the clues. The next 9 lines are the completed puzzle that we can use for reference, and make sure that each number is in the same position as the working table. All right, and the big function for Sudoku is the solve method. So it brute forces backtracking. As you can see here, this is the big method here. It goes through the loop from top left all the way to bottom right. It's going to try from numbers 1 through 9 if it's valid at that cell. So we set it here and we call solve. Solve is also, it's a recursion, so it's going to call it again. If it's valid, we'll show it's valid. Valid checks each constraint row, checks column, and checks the right grid. It returns true if none of these are violated, basically. So it solves all of these. And that's how it is done sequentially. In parallel, it is done a bit differently. It does the same backtracking method as the regular solve, except it calls is valid parallel. Now, is valid parallel is what we decided to do our parallel implementation at. Here we have each over here. Each of them have threads that we launch at once, and we do each of these checks in parallel. Okay, so let's go run one of them. Let's go compile this. Sorry about that. Oops. It's the wrong thing. I have the README here. There we go. So we compiled that. And to run it, if you want to run the Sudoku program, we're going to run Sudoku as the first argument here. And then we need the actual test case. So we have test cases already in here in this folder, as I showed you before. We're going to run Sudoku test1.txt. So this shows the current board as input, the completed board, and then after the current board is solved, we see there is one for the parallel with time for each, and one for sequential and the time for that. Let's try and error case. Let's do test 3. It's going to take a bit longer. As you can see, parallel took this amount of time and sequential took this amount of time. Now let's go through the nonogram. So the nonogram class has different ways of storing the board. It does have the same working board and completing board structure, but the way we store the clues is in different data structures. So nonograms, they can be of n by m dimension, and we could choose that dimension. So let me show you an input file now of a nonogram. This nonogram is, this top row says it's 10 by 10. And the next 10 rows, so from here to 11, I believe, that is the constraints for the row. So like this, and then the next 10 after that, specified by this value here, are the column constraints. And we store them each in a vector of vectors, basically. So row constraints, column constraints are separate. And then finally at the end is the solution for reference. So this scans everything in here. Let's talk about the real juice, the solve method. So we implement DFS here. This is just specifying whether we're doing a parallel implementation or the sequential. Let's talk about the sequential first because the parallel does build out to the sequential one. Parallel starts with the top line, row R. So this is the base case when it reaches the final row, basically, or past the final row, because it's R equals rows. What we do for each row is we generate the possibilities. And possibilities just means every configuration based off the row constraints for this row that we can generate. So find possible rows is also another recursive. Let's go find that. Find possible rows. So it takes constraints. These are for recursion here. Takes the row and it pushes it all to the possibility list. So every possibility is added here basically. And here's all the logic for it, making all the configurations based on the clues. After that's done, we go back to, we run through every row possibility and see if it's valid based on the column constraints. So this is where the column constraints come in. It takes, it checks if each cell up to that point is valid with the column right now. If it is, then it will return true. If it's not, it violates it, it will turn false. And we pretty much prune that dead end. Meaning that recursive line, we just stop there. And then we backtrack, of course. And that is basically the whole logic of the DFS algorithm for a nonogram. Now, the parallel implementation, what we do different is we actually parallelize the possibilities at a certain point. So as you can see here, lower def, upper def, those are set values that we have. We create futures that we push to run asynchronously. And as mentioned before, if one of them, they have like a local solution, so it doesn't worry about like a shared board, so we don't have to worry about locking. They have their own copy, basically. If one of them finds the solution, it's gonna put exchange, that's just a true, to atomic operation. And basically every other thread that's trying to solve it, it's gonna see that, oh, so it's already been solved, we're gonna stop solving for it. And then that's a parallel part. Because it's cumbersome, the overhead of the creation of threads for each possibility, we eventually defer back to the sequential way of thinking, of just going through each possibility sequentially, like this. And having like a hybrid approach to this helps to have our speed a lot closer to the sequential. So I will demonstrate here. Let's run solver with nonogram. Let's run test case. Test cases / nonogram. Let's do 2. And you can see here, current board, completed board, solved board under parallel and sequential.
To test our program, we ran test cases using both a sequential function and a parallel function. Provided in these test cases are an input which include varying difficulty for Sudoku and varying board sizes for nonogram. Once we ran these test cases, we took the runtime and compared the data and compiled them into the bar graphs on the right. Taking a look at these results show that when it comes to solving the Sudoku problems, it was faster to solve using the sequential function rather than the parallel threaded function. When it comes to the nonogram solver, there was a slight improvement in runtime to solve these puzzles with a parallel threaded function rather than the sequential function. Some of the limitations that we faced was the overhead in thread management when it comes to puzzles with a small search space, and our approach stops at the first solution, which may not match the given solution, as some puzzles might have multiple solutions. A trade-off would be balancing thread overhang against speed improvement in complex tasks. For the fastest solution, we could consider a potential for a hybrid model that can switch between sequential and multi-threaded processing. After examining the results, we have come to the conclusion that multi-threading shows mixed results when it comes to Sudoku and nonogram puzzles, with a limited benefit in Sudoku puzzles but being effective in nonogram puzzles. The effectiveness of this parallelization is dependent on the size and structure of these problems. Future directions that we can take include optimizing parallel overhead management, exploring adaptive algorithms that can choose the best method depending on the puzzle complexity, and broadening the approach to solve other types of puzzles. These are our references. Thank you.